Hi, we will discuss the second task of grip tasks for functional data science and business analytics. Our task is prediction using unsupervised machine learning. So what kind of prediction in unsupervised machine learning? We know in unsupervised machine learning we have unlabeled data. So we will use unsupervised machine learning technique, k-means algorithm, to predict the optimum number of clusters in iris dataset and represent it visually. So let's begin by importing our data. We have iris dataset. We can import it to our environment using sklearn library. From datasets module, we see we imported our data successfully. Then we will explore data by using .hit method on our iris data frame. We know now that our dataset have 4 features: sepal length, sepal width, betal length, betal width. So if we use .info method on our iris data frame, we will know that we have 150 entries. We see that we have 4 feature variables. Each variables are measurements of length and width of sepal and betal. The data type of our feature variables is float. The measurement in centimeter. We have no missing value. Here is the linear relationships between our feature variables. We know in unsupervised machine learning we have features only. We don't have target variable. So based on characteristics of our data, we group them or cluster them into groups or clusters. So our prediction here is to predict the number of clusters or groups our data have based on characteristics. So you can think about that we have number of observations from our environment, measurements of flowers. We need to find the number of species in our data. Now we need visuals representing our dataset. We have 2 features, but we can plotting using just the 2 variables. We will use the first 2 feature variables only. Because we have 4-dimensional feature space, we can't plot the 4-dimensional. So we will use the first 2 feature variables only. See here, we plot scatter plot with the first feature on the x-axis, the second feature on the y-axis. Note that we have 4-dimensional feature space, so this visual not represents the whole story. We need to find the number of clusters in our data, the optimum number of clusters. We can implement an elbow function on our data, so we can find the optimum number of clusters representing our data. We see from the plot we can't recognize what the clusters the data will be divided, because we plotting with 2 features only, and we can't plot with all feature space we have. So we need another technique to find the optimum number of clusters in our data. So we can use that optimum number of clusters in our cluster. We have technique named an elbow function. We plot an elbow plot with on x-axis k, the number of clusters we need to find the optimum from them, and inertia in our clusters. What is inertia? Inertia, or WCSS, is within cluster sum of squares. We can find the optimum number of clusters in our data based on the mean of distances between all observations in clusters and the cluster centers. That's the meaning of inertia. We take the value of the sum of squares within all clusters for each trial, saving it on our array WCSS, stands for within clusters sum of squares. The sum of squares within cluster representing inertia within cluster. Low inertia mean tight cluster. So we need the number of clusters where elbow occurs on the line, representing the function of inertia over k, or number of clusters available. We will try with k equal to 1 to 10. We fit our cluster model in our feature space, and we find the inertia by using dot inertia attribute of our model. So if we see in the block which k on x-axis and inertia on y-axis, we have approximately 700 for inertia when we divide our data to one cluster. Already our data in one cluster, but it's the beginning. Increasing k, decreasing inertia, until we reach to k equal 10, where inertia was approximately equals 50. But note, we don't need to reach it to the least possible value of inertia. We need to find the number of species or types in our flowers. Absolutely there will be differences between individuals in each group. So the elbow plot from its name helps us to find the optimal k when the elbow occurs. Here, k equals 3 and the inertia approximately equals 90. What we were doing now, hyperparameter tuning, which our hyperparameter here is our k. So we initialize our cluster with k equals 3. Use our .fit predict method on our k-means model, passing to it our features. If we back again to our last scatter, but with scalars attached to each cluster, and also we draw our centroid or our cluster centers. We have 3 here. We can create cluster centers using .cluster centers attribute on our cluster. You can see some errors here. That's because of 2 reasons. First, because of false predictions of our cluster. Second, from the limitation of plotting the 4-dimensional feature space on 2-dimensional space. So now our cluster model can label data of flowers measurements, but the measurements must be measurements of one of the species we trained our cluster on, Setosa virginica versicolor. The last question here is, can we use that cluster model on classification? We will try it. First, splitting our data to training set and testing set, then refitting our past model, but now on our training set only, and predicting our cluster labels of our training set. We extract our target variable from our dataset, from our original dataset, and save it to y variable. We import accuracy score function so we can evaluate our model on classification, send to it the actual labels and the predicted labels of our training set. We see here the score is 0.091, which is so low. That's because of differences between labels encoding between the cluster labels and the actual labels. So we're using a mapping function to solve that. Here, then call our accuracy score function again, and we get 0.88 for classification on our training data. Now, based on the model fit on our training data, we will predict the cluster labels of our testing data. We call our accuracy score function again. We reach to the same error. We need mapping again, and call our accuracy score function again. We get 0.9 score, which evaluate performance of our clustering model on unseen data. Thanks for watching.